U alpha plus the product over all beta in I of U beta, the power of the compatibility degree between alpha and beta. I'm going to say that's equal to 1. Okay, so generically, well, so that's as many equations as variables. Right, so we've got an equation for each alpha. So generically, well, so as many equations as variables, so generically you might expect the solution to be points. And that's not the situation we're going to be interested in. We're going to be interested in a situation where we get families of solutions. So I'm gonna write U for the space of solutions, and U greater than or equal to 0. So solutions over complex numbers. I'm going to write U greater than or equal to 0 for the solutions for non-negative real solutions. And so notice that if all the U alphas are real and non-negative, then in fact that means that they're all going to be less than or equal to 1, right? Because this term is going to be non-negative, and so something non-negative added to U alpha is supposed to give me 1, so U alpha is in fact going to be between 0 and 1. Okay, so in this non-negative part, we're going to be looking at U alphas between 0. So we're going to be interested in in situations where there's families of solutions, where we U alpha of some parameters y1 to yn is going to be some kind of rational function in these parameters. And to make sense of this product, if the index set is infinite, then this would be an infinite product. And so think of the product in formal power series in these variables, if the index is set. Is it? Okay. And what we want, the sort of interesting thing we're looking for is when the combinatorics of this totally non-negative part of the solution space reflect the combinatorics of compatibility of this function, this compatibility degree C. In the following sense, that the totally non-negative part intersected with the locus where U alpha 1 equals U alpha 2 equals U alpha n equals 0. So U alpha 1 up to U alpha n can all go to 0 simultaneously, and this is non-empty. So this is a thing that can happen if and only if these alpha i's are all mutually compatible. Okay, so this is I mean, I don't know, this may seem like this may not speak to you, but so I'm going to talk about a bunch of examples where this kind of thing is going on, and hopefully some of those examples will be feel a little more. So the first example I want to start with is an example that will be perhaps familiar in physics. So this example is the Koba-Nielsen, goes back to Koba and Nielsen. Back in 1969. And we can think of this indexing set as the diagonals of n plus 3 gone. And compatibility is just, so if I have a diagonal ij and a diagonal kl, I'm going to declare the compatibility degree to be either 1 or 0. 1 if they cross, 0 if they don't cross. Okay, so then this gives rise to a system of equations. U alpha plus the product of the U betas where beta crosses alpha, that's supposed to equal 1. So that's some system of equations. And that's one version of the system of equations that Koba and Nielsen wrote down in 1969. And it turns out that you can solve the system of equations. There's a family of nice solutions to the system of equations. You can write it down explicitly by saying Uij is going to be Z j plus 1 minus Z I Z j minus Z I plus 1 over Zj minus Zi Zj plus 1 minus Z I plus 1. And so you can see this is some nice family of things. These are Zs are complex. If I choose the Zs to be real and ordered, then these will all be positive. So we see we see a nice family of complex solutions. Inside that we see their real part, and then this real part was and this came up yesterday. This is the domain of integration for defining the tree string. So this setup kind of this is sort of kind of fundamental to defining the tree string. So I want to talk about. So in some sense, everything I'm going to be saying is going to be a generalization of this. So I want to think about a generalization that might be more, that might sound like more like cluster algebras for people who like cluster algebras. So this discussed in both papers, Nima, Song, Thomas, me, and then another paper without me. So fix a Dynkin type. The indexing set is going to be what are called the almost positive roots. By definition, the positive roots union with the negative simple roots. And these index the A strip variables. So I'm slightly mixing my notations. It means when people are talking about almost positive roots, this is a notion that comes from Fomin-Levinsky, but I'm also going to want to use sort of Fock-Goncharov language. So I'm going to call the thing that these index the the usual cluster variables in Fock-Gontraf terms be A cluster variables. The compatibility degree is going to be just the usual cluster compatibility. In particular, this isn't going to be symmetric if I'm in a non-simply laced type. That's fine. So there's a again, so like very classic cluster algebra, finite type cluster algebra story. There's a deformed Coxeter element that acts on I, which I'm going to denote by tau. C is already in use, and tau is sort of for reasons, mysterious reasons that will become clear, perhaps. So this is a deformed Coxeter element. This is some permutation of the indexing set. And so again, I mean, what I'm trying to convince you of is that there's a whole family, or there's a whole variety of problems, a whole variety of settings that can all sort of be subsumed under this same general scenario. I told you an indexing set, and I told you a compatibility. So I have in fact told you the system of equations that I want to solve, because I want to solve the system of equations, these U equations that we had on the board at the beginning. So what happened? What do those solutions look like? Well, it turns out there's a way to describe those solutions. Let me introduce another piece of notation. So this is going to be the Fock-Gontraf X cluster variable corresponding. So X cluster variables correspond to mutations of A cluster variables. So this is going to be the mutation when I mutate the beta variable to gamma. That's going to be a corresponding Fock-Gontraf X cluster variable. And the details of this are not so important. I mean, I'm trying to sort of hit several settings, and if a particular setting doesn't speak to you really speak to you, don't worry, we'll be on to something else fairly soon. So the U alpha. So the point is that there's a way to say what the U alphas are. Here they were cross ratios. Here they're going to be, well, this is in fact going to be a generalization of that. These cross ratios are Fock-Gontraf X cluster variables in type A, in fact. So that's also going to be the case here. U alpha is going to be basically just a Fock-Gontraf X variable again. So it's going to be X variable corresponding to the mutation from alpha to the Coxeter element applied to alpha. So basically, this is just a Fock-Gontraf X variable. It's not all of them, because there's more Fock-Gontraf X variables than there are elements of the indexing set. So somehow it's choosing a subset of them. And you can also write this, if you prefer, you can write this in terms of the classical, or the standard sort of A variables. So this is the A alpha, A tau alpha, and up here, this is some monomial, monomial in the A's. Let me not try to say what it is, which is sort of homogeneous in this. It's a cluster monomial. Right. Okay, and so this generalizes the solutions. Yeah. Okay, now, in some sense, oh yeah, okay, right. I want to make a couple of sort of general comments about nice things that are going on in both of these settings. So in both these settings, there's a notion of a G-vector fan. Right, so the compatibility, which was just some compatibility on an abstract set I, there's some way to associate the rays of the fan to alpha in I such that alpha is compatible with itself. So in the settings we've been looking at, alpha is actually always compatible with itself, but that's not guaranteed. And if alpha is not compatible with itself, it doesn't correspond to a boundary. It shouldn't correspond to a ray. But so in these settings, we do get a fan. And so there's some sort of some additional natural structure of a fan. It's also dual to polytope described as a Minkowski sum of small pieces. And yeah, so there's sort of so what I want to do next is to explain a kind of general setting that present a general setting that explains a kind of origin story for both of these things in terms of finite dimensional algebras. So this is the collaborators I was at the beginning. So a finite dimensional algebra and for now, at least, I'm going to assume it has only finitely many indecomposable representations. I'll say a little bit more about what that actually means here. So I'm going to think of A, in fact, as something of this form. Something like that. So Q is a quiver. That just means a directed graph. CQ is just the path algebra. So that's just an algebra whose basis is the paths in the quiver Q with the product given by concatenation. And then R is some relations. So these are just some particular paths. The R in brackets is the ideal generated by these relations, which we're quotienting out. And so we're interested in modules over this finite dimensional algebra. But the nice way to think about modules over a quotient of a path algebra is as representations. And I want to take a moment to explain what those look like, because they are actually very concrete, explicit things, and very easy to work with, in fact. So finite dimensional modules really correspond to representations of Q satisfying relations are, I'll explain what I mean by that. So a representation of Q is just an assignment of a finite dimensional vector space to each vertex of Q and a linear map between the corresponding vector spaces to each arrow. Okay. So there's a natural notion of direct, okay, and then what I mean when I say satisfying the relations are, I just mean that there's some relations, there may be some relations that the linear maps satisfy. So there's a notion of direct sum, which is just sort of the natural thing. If I have two representations, I can take the direct sum, that gives me another representation. And the notion of indecomposable representation, so X is an indecomposable representation if X is not isomorphic to a non-trivial sum. So in particular, if we take the very simplest looking quiver, it's just a bunch of arrows linearly oriented from 1 to n. An indecomposable representation of this quiver, it's pretty easy to convince yourself that if I have some vertex I, if I choose some substring starting at some vertex I, going to some vertex j, I put down a copy of C at each vertex between I and j. I put say maps which are multiplication by 1 going between successive copies of C. It's pretty easy to convince yourself this is indecomposable. In fact, this is all of them up to isomorphism. So and isomorphism here means base change, and so in fact these numbers weren't very important. After base change, any non-zero scalars would have worked just as well. But there's something non-trivial here that in fact every representation, whatever dimensions, can in fact of this quiver can in fact be written as just a direct sum of guys that look like this. And so what is this leading towards? This is leading towards the fact that this looks a lot like the combinatorics from 1. Right? I mean, there we had diagonals in an n-gon indexed by, let's say, I and j. This looks awfully similar. It's not exactly the same, but it's awfully similar. If Q is any Dynkin diagram, actually, let me make it simply ways. So A, D, E, with any orientation, like you can type A diagram like this, but I could change some of the directions of the arrows, or I can think about type D or type E. Then the indecomposable representations of Q correspond bijectively to the positive roots. So this is Gabriel's theorem. Positive roots of the root system. And so again, the indecomposable representations of this quiver are corresponding to the positive roots. That's almost what we were interested in setting 2. Remember that setting 2 is coming from cluster algebras. There, the indexing set was the almost positive roots. Here we had positive roots. So there's a little something missing. And if you think about it, also in this setting, there's not quite enough to match up perfectly with setting 1. How do we make that work? Well, in this general setting of finite-dimensional algebra, let me suppose vertices of Q are just 1 to n. My indexing set in this general setting, which is going to extend settings 1 and 2, the indexing set is just the indecomposable representations of A. So that's more or less what we've been talking about, together with something that corresponds to the negative simple roots in the cluster setting. So, so this is an additional object, which, like for sort of one reason representation theorists might write down like this. So this is so there's sort of n additional objects. You should feel like these are like the negative simple roots from cluster theory. And you shouldn't worry too much about what it means. You can think of this as just a very much formal gadget. There is also, if you like such things, you can write this in a way that makes you sound smarter. You can call this the homotopy category of 2-term complexes of projective modules. And there's a fancy notation that you can write down. Yeah. So anyway, don't worry too much about that. But there is, anyway, this is just to say there is a sort of fancier way in which these extra guys actually appear naturally as just on like an equal footing with everybody else, which is maybe not surprising that there should be some way of doing that, where instead of thinking about the negative simples as sort of special things that get added, in fact, there's a way to present the whole category where everybody placed here. Right. So I'm busy describing my general setting. I should tell you what the compatibility degree is. For people who are familiar with cluster algebras, this is the E invariant of alpha and beta. Yeah, and let me just say in alpha beta plus in beta. So how here is the Auslander translation. How takes the indexing set to the indexing set, but it kills some of them. Say too much about that, but this is that's not good. Plays an important role in the study of representations during the finite-dimensional algebras. So in this setting, I would like to explain explain how one can write down the solutions generally to this system of equations and get nice nice solutions that you solve the U equations in a general setting, which reproduce the solutions in the earlier settings I was discussing. In order to do that, I need to introduce F polynomials. So for alpha in I, there's some F polynomial. So this generalizes the F polynomials from cluster algebras. This idea was introduced by Dirksen, Wayman, and Zelodinsky, really with a view to essentially categorifying the F polynomials from cluster algebra here. So this is a sort of categorical perspective which allows you to recover the F polynomials from cluster algebra, but it's defined in this much more general sense. So for alpha being one of the shifted projectives, we just say that F alpha is 1, so that's just sort of boring. So the meat of the matter is what is the F polynomial when alpha is an honest representation. In this case, F alpha is defined to be a sum over dimension vectors of something which looks a little scary, but I want to try to convince you that it's not really so very scary. So there's going to be a sum over dimension vectors of this y to the d, by which I mean y1 to the d1, yn to the dn. And so this is just some well, I mean, it's some like formal power series counting something, but in fact, it's just a polynomial. I mean, I wrote it as if it was a formal power, as it was a power series, because I wrote it as a sum over all possible dimension vectors. But in fact, the d's here are going to be less than the dimension of alpha itself. So this is just going to be actually a polynomial. What it's trying to keep track of is the sub-representations of the representation alpha. So well, okay, let me finish writing that, and then let me say what this is. So GER D alpha is the space of sub-representations of alpha of dimension D. And this phi is the Euler characteristic. So, I mean, this is, so Euler characteristics are a little bit scary. But in lots of nice situations, this Grassmannian is actually just a single point or is empty. And so if it's empty, then the Euler characteristic is 0. And if it's a single point, then the Euler characteristic is 1. So in fact, that's really all you need. As an exercise, you can recover the F polynomials from this situation, so the Dynkin type A F polynomials, you can recover from this definition. As a little exercise, you'll find that the spaces of Grassmannians involved are all points or empty. And so in this way, you get the usual F polynomials if you're used to what those usual F polynomials are. So in this case, so using these F polynomials, we can write down solutions. So U alpha is 1 minus y to the dimension of alpha over, it's 1 minus y to the dimension of alpha over f tau alpha. And you can also write this as just some ratio of f's if you prefer some other f's. So this is some sorry, I'm being a little vague about that, but this is fine. So there's a solution. There's a family of solutions you know, where you know, family, in terms of these y's, you know, you can set the y's to be whatever you like, and you get a solution. And this provides you know, a solution that has all the beautiful combinatorics that we want, the non-negative solutions. This u greater than or equal to 0 space has exactly the combinatorics of compatibility in this setting, and this recovers the storage from the settings 1 and 2 that I was talking about before. I've lost track of when I started and when I was supposed to stop.
You have 15 minutes.
Oh, well, okay, thank you. Right. Okay, so in particular, yeah, so in this setting, there is also a G-vector fan. So the G-vector of an indecomposable or G-vector, so it's saying there's a G-vector fan, which generalizes the G-vector fans we've already seen. So the G-vectors encode minimal projective presentations of the indecomposable representations, and this fan is dual to a Minkowski sum of the Newton polytopes of the F's. This is by a result of Jarry Fay. So we sort of get, and so this is kind of the general story that I want to advertise, which is sort of most worked out in this case, where we have a finite dimensional algebra with finitely many indecomposable objects. Sort of everything works perfectly. Now, I want to just say a couple of words about one particular setting where we recover some combinatorics, some more combinatorics. That's also kind of interesting. So, so some sort of a combinatorial setting that's been studied by Liavsky, Pearson-Spire, Santos-Sturm-Welker, Anvil, and that I am working on with Nick Early, working on applying this general sort of story to understand. So the setting here, the indexing set here, is going to be lattice paths from 0k to n minus k 0. So these are just lattice paths kind of going like that, ending and starting over here, ending up over there. And we have a notion of compatibility. And so this is supposed to, well, and sort of this combinatorics, as I said, has been well studied, and it generalizes combinatorics of so the compatibility degree is the number of kisses. So two paths kiss if they come along like that, they join together for a while and then they depart again. So this is a kiss. It's not a kiss if they come together and they leave, but they've crossed each other. So that, right, so in this kiss, the orange path, there's the common part, and then when outside the common, or just outside the common part, the orange path is below and the yellow path is above. That's a kiss. Twice. This is not a kiss because the orange path is below on the left-hand side, but above on the right. Okay. So you can define this combinatorics. And so it turns out that this is all beautifully encoded by a particular finite-dimensional algebra. And so I'm just going to graph it with a sketch what the algebra is. And so this is also related to, physics by a technique, which but yeah, so the algebra just looks like this sort of grid, and then these dotted lines correspond to relations that are length 2 relations that say that the composition of this arrow with this arrow is 0, the composition of this arrow is 0. So basically, wherever okay, so wherever there's like an arrow followed by a turn and an adjacent arrow, those are all supposed to be 0. So that gives you a lovely algebra. It's a finite dimensional algebra. Has only finite many indecomposable representations. They together with the shifted projectives, the weird negative simple guys, correspond to lattice paths, and you get the whole combinatorics of this whole non-crossing lattice path combinatorics out. And you can get various other things. There's people have thought about like the Grassmannian order in this setting. You can get that out of the representation theory as well. There's like lots of stuff you can get out of the representation theory. Okay, let me quickly say something about surfaces.
Can you say what Minkowski sum of polytopes you get for this example?
Yeah. I mean, so they're going to be the Newton polytopes of the F polynomials. The indecomposable representations just look like something, you know, so the indecomposable representations are just these string modules. They're just like something like that. And then, you know, so you know what the sub, I mean, so the submodules are just sort of the obvious things. If you think of this as like a mountainscape, it's just the lower parts. Anyway, there's sort of an obvious thing, and then that's the and those are the polytopes that you need. Yeah, so in particular, yeah, this realizes
They're all simple, they have nice common.
Does it have a
really?
I mean, that's what Santos called
The small ones though? No, not the summands.
No,
Yes.
the whole thing.
The whole thing, yeah, but no. I mean, I think Thomas was asking about the summands. I don't know that there's a name for the summands. So let me quickly say something about surfaces. So we have a surface, M set of marked points on the boundary. I'm going to be cautious and not allow marked points in the interior. Sorry. My indexing set is going to be curves from boundary to boundary, avoiding points. My compatibility degree is going to be number of crossings. Actually, this is okay. And there's a beautiful correspondence from surfaces to gentle algebras. So this, I guess this really gets going with work of Haydn, Koba and Nielsen, but was developed by a number of other people, including my collaborator Pierre-Guy and some of his collaborators. So from the surface, you can associate a gentle algebra, and now you can, basically do the same setting of part 3. The algebra is going to be typically infinite representation type, and that means that the proofs require a little bit more care, but everything does go through because basically gentle algebras are good to work with. The final thing that I want to say, I guess, is B. We could include surfaces. We could include closed curves. And I'm not going to sort of give all the details of what I mean by that because I'm running out of time. But to a closed curve, C, there's a corresponding family of representations, M, C, lambda, R. Lambda is a non-zero scalar, and R is a positive integer. The non-zero scalar doesn't matter. We can just ignore it combinatorially. It doesn't make any difference. The scalar is important, though. So yeah, this thing has a well-defined G vector. That is outside the G vector fan. And the reason I particularly wanted to mention this is that, so the individual, if I look at these modules and I look at their corresponding U variables, well, they are not self-compatible. And if you just write down their U equations, you see that they don't contribute boundaries, but it turns out that you can package them together in a way that is natural. You can think about product U, C, R. I'm just suppressing lambda because lambda didn't matter. So I'm packaging the U's corresponding to different ranks together, and for some reason taking to the power R, which I can't explain very well, but there is sort of a representation theoretic reason to want to do this. If you do this, you get something that looks like 1 minus A minus square root of B over A plus square root of B. So I was inspired so I wound up spending a bunch of time last night trying to get this to actually exactly match Mark's talk from yesterday. I didn't manage to make it, I didn't quite get there, but it should be possible. It's like pretty clear that the pieces all the necessary pieces are there to figure out how you can get exactly the expression that looked like this in Mark's talk that's coming from the cluster algebra for Grassmannian from a suitable representation theoretic perspective. You should be able to get something, and I'd be astonished if the corresponding product, which looks exactly like this, didn't yield exactly those sort of mysterious quantities that were not coming from cluster variables for Mark. I think they should be coming exactly like this.
What's this notion of ranking?
Well, so there is a these are band modules, and just the way that band modules are parameterized, there is this R that enters.
It's not attached to the curve,
I mean, I guess, I think that the thing you say, if you want to sound smart, is I think you call it a local system on the curve. But so it's a rank R, so it's some kind of rank R thing attached to the curve. Yeah, I mean, there's something, it's sort of you're choosing so these indecomposables are corresponding to like a single Jordan block. And so there's a choice of an eigenvector, or of an eigenvalue, which is the lambda, and there's a choice of an R, which is the size of the Jordan block. So these are, oh yeah, sorry, this is like, I'm sorry, the thing I should say to you is you know, this is like, well, this should be corresponding to like thinking about going several times around the curve. I mean, some kind of, you know, these are bracelets or bangles
also
or.
like the number of times.
Yeah, it's going the number of times going around. Yeah, for me, I mean, for the representation here, you shouldn't think of it exactly as you shouldn't literally think of it as number of times going around, but yes, it's that kind of, that's what it is. Anyway, yeah, so I'm out of, I should stop there. Thank you.